Hello and a very warm welcome to part 3 of the Stereochemistry course. So lastly we talked about geometrical isomerism, how do we specify geometrical isomerism, and then we talked about EZ nomenclature and also we talked about CIP rules. I gave you some homeworks to do, so let us finish those first and today we'll start optical isomerism. So let's look at this. I hope you guys have done this. So if you have not done this, if you have not looked at the last video, do go back, look at the part 2 of Stereochemistry course and then come to here. Then only you can maintain the continuity and you can understand what we are looking for here. So let us look at the first problem then. Okay, the question says specify if the following shows geometrical isomerism or not. Now what do I say when you have a double bond? When you have a double bond, the only thing which shows whether you have a geometrical isomerism or not is if you have two different functional groups attached to it. Let us see if this double bond has two different functional groups attached to it. One side we have a hydrogen, okay, and another side we have a CH2Me, which is we have an ethyl. So on one side we have a hydrogen, on the other side we have an ethyl. So different functional groups are attached to it. So it will show geometrical isomerism with respect to this bond. Now we also learned in the last class that if we have different sides, you have to check all the sides if they show geometrical isomerism or not. Like if we have a ring and a double bond, we have to search that whether with respect to the ring it will show geometrical isomerism. Again, with respect to a double bond, whether it shows geometrical isomerism. Now, this molecule has two sides to show geometrical isomerism. This double bond and this double bond here. So, we also have to check with respect to this double bond also. Okay, let us check with respect to this double bond. Let us write the hydrogens. We have a hydrogen here, a hydrogen here, a hydrogen here. And what do we check in case of a double bond? Whether different functional groups attached to it. We don't need to check anything else. If different functional groups are attached to it, it will show geometrical isomerism. So let us look at this. We have a hydrogen and a vinyl competition here. In this side, we have a hydrogen versus hydrogen competition. That is, same functional group is attached to it. Thus, the molecule will not show geometrical isomerism with respect to this double bond. With respect to this double bond. This double bond. You see how the difference lies? So in all the sides, in all the possible sides, you have to check whether it will show geometrical isomerism or not. See, in this molecule, it will show geometrical isomerism with respect to one double bond, but with respect to the other double bond, it will not show geometrical isomerism. I hope you have got that right. Let's get to the next molecule. Next molecule, we have a cyclohexane ring with 4 fluorines attached to it. Now, one of the things is how many fluorines is attached to it doesn't matter. Well, I told you in last class, in a ring, you only check if you have an sp2 center. If you have an sp3 center, it will always show geometrical isomerism. In case of an sp2 center, the situation becomes complex, but still it can show geometrical isomerism. Okay, let us look here. We can have this fluorine at the top of the board and a hydrogen below. And the same case can happen in all the 4 fluorines. That means that is one isomer. Another thing can happen is 3 of the fluorines are on top and 1 fluorine is below. That can also happen. So it can show many such isomers, and these are all geometrical isomers because we are looking with respect to the ring and we are not changing the molecule. As I explained, it is restricted rotation. Thus this molecule will show geometrical isomerism with respect to the ring again. But here there is only one side, so we don't need to understand whether we have other sides or not. So in a ring, first check whether we have a sigma bond. If there is sigma bond, then just see that we can have different isomers where the positions of the substituents can be different. That's it. Okay, let us look at this third molecule then. Now remember this molecule we did in the last class? We had some methyl, hydrogen, and we told when we have a double bond, we draw a straight line through the double bond and we divide this ring into 2 parts. Okay, this is the same molecule, so we draw a straight line through this double bond, right? Now it looks similar to the cyclopropane case, to this case, right? So we draw a straight line through this fluorine and through this double bond. Now let us look at both the sides. Okay, I see it here. We have a CH2, In this case also we have a CH2. And here we are looking with respect to the double bond. Okay. Now again with respect to the double bond, what I said that different functional groups must be attached to it. Here we have a hydrogen versus methyl competition. Fair enough, different functional groups attached to it. But in here we have a CH2 versus a CH2. So it is the same functional group attached to it. So this will not show geometrical isomerism. Got my point? The next 3 are all similar. How is it similar? We have a double bond in the ring Now this is on top, this is also on top. They are on the same side. So this is a cis isomer. And as I said in last class, till 8-member ring, it is not possible to have a trans isomer. It is possible, but it is highly strained in energy. So till 8-member ring, you will always see cis isomer. We have a cis isomer with respect to the double bond. So this will show geometrical isomerism with respect to the double bond. Will show geometrical isomerism. Again, we have two substitutions. This is methyl is here and a chlorine is here. This methyl can be top. There is a hydrogen here. We can have chlorine top and a hydrogen. Another isomer could be the methyl is below, the chlorine is top. That is also another. So this will also show geometrical isomerism with respect to the ring as well. So this will show geometrical isomerism with respect to this double bond. If you can do 4, 5 is same. Nothing, don't just panic about the same substitution or different substitution. We are not looking at the plane. This is a geometrical isomer. Many may say, okay, this is a plane, that the top half of the molecule is same as the bottom half. We'll come to that in this video. But right now we are talking about geometrical isomerism. So just look at the rules I told in the last class. See again, this cis isomer with respect to double bond. Again, with respect to double bond, what we see, that we have different functional groups. We have a hydrogen here. Hydrogen versus this competition, this CH2 CHMe. Again, hydrogen versus this competition, we have different functional groups on both sides of the double bond. So it will show geometrical isomerism with respect to the double bond. Will show geometrical isomerism. 5 if we have done, 6 is also the same. Only thing is that here the geometrical isomerism will be only with respect to this double bond. Again, it is cis isomer. Again, it is a competition between hydrogen CH2. So different functional groups. So it will show geometrical isomerism with respect to the double bond. With respect to the ring, we don't have two substitutions. So we can't compare the chlorine we have here with some. I hope you have got this right. Another part I gave is the EZ versus Z nomenclature. I hope you have done it. This is much easier. As I said, you just have to remember the CIP rules. Okay, let us do one by one. We have ethyl versus fluorine competition. The first rule says the higher atomic number gets the preference. Fluorine has a higher atomic number compared to CH. So fluorine gets the preference. So this is 1, this is 2. Let us number because I like the numbering. It becomes easier. Again, we have a chlorine versus propyl competition. Chlorine versus CH2 competition exactly. Like what is propyl? And propyl CH2, CH2, CH3. So we compare this chlorine and this CH2. Chlorine has a higher atomic number. So chlorine is 1 and propyl is 2. And what we know, if same priority groups on the same side of the double bond, it is a Z isomer. If same priority groups are on the opposite side of the double bond, it is a E isomer. Here they are on the same side of the double bond. So this is Z. I hope you got that right. Okay, let's look at this molecule. Now, okay, let us look at first this one. Now, this molecule is there in the last example as well. And when a molecule does not show geometrical isomerism, it does not succumb to E versus Z nomenclature. This is something you also have to remember, that E versus Z nomenclature is only possible when they show geometrical isomerism. Like here, we have a hydrogen, both the functional groups are the same. So here E versus Z nomenclature is null and void. It doesn't have any meaning. But there is another double bond. So we have to check with respect to this double bond, whether we have a E or a Z nomenclature. Okay, let us point it out. Here we have hydrogen. Okay, let us see. We have a hydrogen and an ethyl competition. This is CH2Me, ethyl. So carbon versus hydrogen competition. Carbon comes before. Carbon has a higher atomic number than hydrogen. Carbon comes first. So it gets first priority. So this is 1. This is 2. Okay, let us look at here. We have a methyl versus vinyl competition. So what is this? This is a methyl versus a CH2 CH double bond CH2. You can see clearly here. You can see clearly here the carbon is attached to 3 hydrogens, while here the carbon is attached to 2 hydrogen and a carbon. So this will get preference, as I told last time before, that carbon attached to carbon gets preference compared to carbon attached to hydrogen. Remember the CIP rules. Don't forget the CIP rules. Those will come in handy even in RNS nomenclature as well. So this will get preference. This CH2 CH double bond CH2 is allyl group. So this is 1 prime. This is 2 prime. Check here. The priority groups are on the opposite side of the double bond. So what is it? It's an E isomer, right? I hope you got that correct. Mark yourself if you got it correct. Okay. Let us look at the next one. This is same as this one. Again, this double bond doesn't have any role in E versus Z nomenclature because it is not a geometrical isomerism with respect. It does not show geometrical isomerism with respect to that double bond. We only use E versus Z when that double bond has a geometrical isomer. So let us look at this one. Okay, so this is the same example as the last one. So I just put the hydrogens. So we have a hydrogen versus ethyl competition, same as the last one, same as this one. So this gets preference 1, this gets preference 2. Now we have a bromine versus a CH2CH, that is an allylic competition. Now as I said, you go to the second atom if there is not a conclusive evidence from the first atom. But here see the bromine versus the CH2 competition. So we don't need to look at this part. We don't need to look at this part. We can only conclude from the CH2 versus bromine. Bromine has a higher atomic number. So bromine versus CH2 will give bromine as the first one. So this has the first preference, 1 prime. This is 2 prime. See the same priority groups on the same side of the double bond. So it is again a Z isomer. See how it is different. Just changing one substituent, it changes from E to Z. Here we had a methyl at the same position. This is the same molecule. Only there is a change in methyl and bromine. When we had a methyl, this was an E isomer. As soon as we change to bromine, it becomes a Z isomer. That is how important E versus Z nomenclature is. Okay, let us look at this one. We look at E versus Z only with respect to double bond, not with respect to ring. Okay, let us look at here. So we have, let us look at this side first. We have a COOH versus CH2OH competition. I'll write here. COOH versus CH2OH competition. So let us look at both the molecules. This carbon has an oxygen attached to it and another OH attached to it. This carbon has 2 hydrogens attached to it and an OH attached to it. Now you tell me which one will get preference. Obviously this one, because it is an oxygen attached to it compared to a hydrogen. Oxygen has higher atomic number, so this will get preference. So this is 1. Let us look at the bottom one. Okay, you have a CH2 here, a CH2 here. Okay, same. We can't distinguish. Then we go to the second atom. We have a CH2 here and a CH fluorine here. CHF here. You tell me which one will get preference. Here we have a conclusive evidence, right? CH2 versus CHF. Obviously the CHF will get preference. So this branch will get preference. So this will be 1 prime. This will be 2 prime. So 1 and 1 prime are on opposite sides of the double bond. This is an E isomer. Higher priority sides on opposite side of the double bond. It is an E isomer. Okay, let us look at number 5 then. Okay, I'll draw this number 5. Remember the double bond, triple bond rules I told? Let us draw it like that. So this is the double bond with respect to which we want to understand. So we have N. Remember how we drew C double bond C, or what we call as nascent carbons. So this is nitrogen. This is, I'll just put 0 because these don't exist. This is C triple bond C. So I'll just put this nascent symbol so that you understand how these come. And down we have a CH2OMe. Okay, let us compare the left hand side first. We have a nitrogen, fair enough. Now we have a nitrogen which is attached to 2 carbon atoms. Here we have a nitrogen which is attached to 1 carbon atom only. Straight away here we get the preference. Oh, this is 1 and this is 2. Understood why? Here the nitrogen is attached to 2 carbon atoms, while here the nitrogen is attached to 1 carbon atom and a hydrogen. Nitrogen, hydrogen, carbon, and a nitrogen, carbon, carbon. Obviously nitrogen, carbon, carbon get preference, right? So that is 1. Okay, let us look at this one. Here the carbon is attached to 3 carbon atoms. Here the carbon is attached to 2 hydrogen atoms and an oxygen atom. Now which is higher atomic number? As soon as you get to higher atomic number, that will get preference. Oxygen has higher atomic number compared to carbon. So even though you have 3 carbon atoms attached to it, but as soon as you have a higher atomic number, that will get preference. This is very important. This type of confusing things comes in exams. This comes like you have 2 hydrogens and an oxygen. On the other hand, you have 3 carbons. Okay, then how will I compare? Carbons and hydrogens we can compare, or we can compare carbons and oxygen. We'll always look at the highest atomic number. Here in this case, we have an oxygen versus carbon competition. We forget the hydrogens, we forget the other carbons. As soon as the oxygen comes, we have oxygen versus carbon competition. Oxygen is higher atomic number, so oxygen gets the preference. So this side becomes 1 prime, this becomes 2 prime. Higher priority sides on opposite side of the double bond, it is an E isomer, right? I hope you got it. Let us look at the last one then. Okay. Here we have a chlorine butyl competition. Simple. Fluorine higher atomic number will get the preference. So 1. We have done this before, so I'm not explaining much. 1, 2. Let us look. So we got this side. This is 1. This is 2. Let us look at this side. Let us look at this side. We have a CH2, a carbon which is attached to 1 carbon, 2 carbon and 2 so this is CH. Sorry, CH. All of these are CH. Okay. This carbon is attached to 2 carbons and a hydrogen. Here the carbon is attached to 1 carbon and 2 hydrogens. Straight away you have a preference. Why? In here the carbon is attached to 2 carbons, while in the next case the carbon is attached to 1 carbon and 2 hydrogens. The carbon will get preference over hydrogen. Remember? So this is 1 prime. This is 2 prime. The higher priority groups on the same side of the double bond. It is a Z isomer. Z isomer. I hope you got all of them right. If you haven't, if you have any confusion, especially in the last two, they may confuse some of you, do contact us. We will be free to help you and explain you again. So having this, we will start today with optical isomerism. Now what is optical isomerism? Why optical? We talked about geometrical isomerism. We are done with mostly geometrical isomerism. Some little bit things are left. I will talk about when we talk after RS nomenclature. A molecule will show optical isomerism, or a molecule is optically active if it does not have any plane or center of symmetry, or it is asymmetric. That is, it does not show symmetry. As soon as it shows symmetry, it becomes optically inactive or achiral. So a molecule becomes chiral only if it is asymmetric. If you have symmetric things, it does not remain chiral anymore. It becomes achiral. So asymmetry, that is breaking the symmetry, is required in order for a molecule to become optically active and in order to show optical isomerism. So, but before we go to optical isomerism, let us read what we have. A molecule is said to be chiral, or a molecule is optically active if it is asymmetric. What is asymmetric? A molecule is asymmetric if it has no plane or center of symmetry. Then you can ask, what is plane or center of symmetry? Let's look at this. If a molecule has one or more symmetry operations, then it is optically inactive or achiral. What is symmetry operations? This plane or center of symmetry are symmetry operations. So today we will talk about symmetry operations. These are important when we go forward. Okay. So let us look at them. First of all, I start with the easiest one, center of symmetry. What does it state? First of all, a molecule has a center of symmetry when for any atom in the molecule, an identical atom exists diametrically opposite that center and equal distance from it. What do you mean? Suppose you have a football stadium. This is a football stadium, suppose. These are the corners. I hope you have watched football, everyone. These are the corners. So I say this is the center where the kick starts. So if I say that this is the center, that means from this corner, if I draw a straight line, I can reach that corner. And I'll say that this corner is same as this corner, or is equivalent as this corner. Identical. Okay. So if I say in chemical sense that if I have a methyl here and this is my center of the molecule, then if I draw a straight line from this methyl to the center of molecule, and if I extend it further from the center towards the other side, it should reach a methyl towards the other side. Then this point where I draw this dot is called the center of symmetry. That is, it is an imaginary point in the molecule whereby if we start a straight line from any one of the corners of the molecule, if we continue the straight line to the center and again extend it, at the end of that straight line we will encounter an identical atom. What do I mean by identical atom? If I start with methyl, we will end up having a methyl at the end. So that point in the center is called a center of symmetry. Okay, let us look at the examples. Football won't help us in chemistry. Okay, let us look at this one then. If I say this is the molecule and if I say this is the center. Now, whenever I talk about the symmetry operations, always remember that you choose the symmetry operations, plane of symmetry if I talk about later, center of symmetry, or I'll talk about axis of symmetry a little bit. Whenever we choose the symmetry operations in such a way that it is symmetrical, that is our whole point, right? We have to make the molecule optically active. So we have to break the symmetry. How do we characterize the symmetry first? By symmetry operations. So whenever we choose the symmetry operations, we choose it in such a way that we find this molecule symmetrical. We don't choose the center somewhere here because this will not keep it symmetrical. This is outside the molecule. we will not make it symmetrical if I choose a center of symmetry outside the molecule. So remember students, whenever you choose a symmetry operation, any symmetry operation for this sense, you should choose it at a point or an axis which makes the molecule, or which divides the molecule into symmetrical halves. Because symmetry is all we are looking for here. Okay, let us look at this center if I see. So if I draw a straight line from this OH passing through the center, see it encounters an OH exactly on the other side. It satisfies, so it is a center of symmetry. This is what I am talking. So choose a center of a molecule in such a way that if we start drawing a straight line from any one of the groups and pass through the center and extend it after passing through the center, when it will reach the end of the molecule, it will encounter an identical atom. See, we started at the OH, it passed to the center, we extended the line, it encountered another OH. So that's why this is the center of symmetry, or we call as CoS. It's a short form. Let's see the methyl then. We start from the methyl, we pass to the center, see we encounter identical methyl. Now I may say that, okay, I may have a molecule like this. OH, both OH are on top. And suppose I say both methyl are also on top. Will this same center be a center of symmetry? No. Because if I start from this OH, it should only reach that 3 position when the OH is below the molecule. You can't go from here and pass the center and say, okay, I draw a straight line and this reach this OH. So this is an important thing, remember. In a molecule, in a cyclobutane ring, if 2 OH are on top of the plane and if we consider the center to be the center of molecule, it will not be a center of symmetry. We must start from this molecule and draw to a straight line. We can't just curve the line and say, okay, it is the center of symmetry. It must be a straight line. Only if we draw the straight line and reach an identical atom, then only we will say, okay, it is a center of symmetry. Let us look at the next example. As I said, if I say I draw a point here, and I start from the OH, can I reach this OH? This will continue to here. Like if the hydrogen is there, it will continue to hydrogen. So then this molecule doesn't have a center of symmetry. This is not the center of symmetry. So this molecule does not have a CoS. This is very important when you understand the center of symmetry. You should always remember the symmetry. You should draw a straight line and it should not break. You should not curve the line or to reach the other molecule. You should see that if a straight line can be drawn so that we can reach the other molecule, and other molecule should be identical. Let us look at the next one. This molecular center of symmetry, benzene. This is very easy. You draw a center here. Any of the hydrogens, since it is not substituted, any of the hydrogens start drawing a straight line, it will make another hydrogen. This is very easy. Okay, let us look at this one then. This is very important. Okay, let us look at this one then. Okay, suppose we have, this is our cyclohexane ring. And we have the methyl here, and the 4 position, suppose the methyl is below. And this we call the center. So if I start drawing a straight line, this is one methyl. Okay? And this is the other methyl. Suppose 2 and 4, 1 and 4 position at their side. So I start drawing a straight line from this methyl. It passes to the center and goes to the below molecule. That is, if we have a methyl top at the 1 position, only if we have a methyl at the below the plane, the 4 position, then only we have a center of symmetry. So this molecule has a center of symmetry. The situation changes as we have this molecule. Now see, both the methyls are on top. See, this methyl is also on top. This methyl is also on top. How can we draw a straight line which starts from this methyl, tip of this methyl? Suppose we draw a straight line, it will always pass the center and go an identical distance to see below the plane. But below the plane there is hydrogen. It doesn't encounter a methyl. So this center, in both the cases, this is the center. This center is not centrosymmetric, is not a center of symmetry. See, this has a center of symmetry. This doesn't. This is center of symmetry. This is the simplest symmetry operation you can understand, okay? It will go tougher from now on. Center of symmetry is very easy. If you don't remember anything, just remember football field. Just remember the corners of it. If you have two different same substitutions, suppose 2 methyls at 2 exactly diagonal corners, Then the center is a center of symmetry. The point where the football starts kicking, the center of the football field is a center of symmetry. In this way, remember center of symmetry. Always when an examiner gives you a question and tells, okay, if this molecule is center of symmetry or not, always start drawing a straight line from that tip. As I drew here, start drawing a straight line from this tip, the tip of the methyl. Sometimes it may happen that if we don't draw a straight line, we will say, okay, this molecule is center of symmetry, but this molecule does not. As soon as you start drawing the straight line, you will understand that the straight line has to go below the plane in order to encounter an identical atom. That's why this molecule is a center of symmetry and the other molecule does not. Let's go to plane of symmetry. What is a plane of symmetry? A plane of symmetry is an imaginary plane, which, if it exists, it's an imaginary plane. We are imagining the plane. Such as we divide the molecule into two symmetrically equal parts, one part being the mirror image of the other. That is, if we have a molecule, if this is a molecule, we draw a plane to the middle. Again, why middle? Because we want to create symmetry. We want to maintain the symmetry. So symmetry is a main point. We imagine the plane. These are all imaginary operations. These are not like nobody will break a molecule and give it to you. These are imaginary operations. So you have to understand that this is an imaginary plane, and you imagine the plane in such a way that it divides the molecule into symmetrically equal halves. Symmetry, it will maintain the symmetry, remember? So such that one half is a mirror image of the other. Okay, let us do the simplest example we know, water. We know this is the shape of water. We don't consider lone pairs because lone pairs we don't consider in these symmetry operations. Another thing you must remember is these are like spherical balls. Okay, in the plane only one half, like these are spherical balls like this. These molecules are all spherical balls. So in the plane only half of the spherical ball will be here. The other half will be in the other side of the plane. Okay, so if we suppose this is the plane, or like this is the plane, here the OH, the half of the oxygen will be here, the other half will be on the back side. Like it is not below the plane, it is in the plane only, but from your point of view you can only see half of the ball. Put the ball like this in front of your hand, you will only see half of the ball. So these molecules are all spherical balls. Okay, let us see this one, water. Here, water. Let us mark this 1, we have this 2. How do we imagine a plane or a plane of symmetry in this case? As I say, whenever you want to imagine a plane, we should imagine the plane such that it makes symmetric, makes the molecule symmetric. We can imagine a plane here passing through the oxygen atom. If you imagine a plane that passes through the oxygen atom, the hydrogen atoms will interchange positions. So if this is the imaginary plane, we are dividing the molecule into two halves such that both the halves are same and one half is a mirror image of the other. So this is the plane of symmetry of water. Now as I said spherical balls, and when I consider a planar molecule, that means if this is a spherical ball, I can have a plane here which divides each of the molecule into half. Suppose I have, this is the spherical ball, I suppose. Okay, this is my oxygen, suppose, just for example. So I can draw a plane here which divides the oxygen atom into two parts. Either one part is a mirror image of the other. Like this part of oxygen is same as this. We'll have oxygen on both sides. This only happens when you have planar molecule. If we have something above the plane, then we don't see the half of the ball. We see the full ball, right? If we have this, it's okay. But if we are seeing from above, then what you are seeing from your side, you are seeing the full molecule. But if you are seeing in the plane, you are seeing only the half of the ball. Like it is coming like this. Half of the ball, right? So in all planar molecules, the molecular plane is also a plane of symmetry. This is the molecular plane. This is how it resonates in 2D. It is like this. Like this is the water molecule. The plane will like cut like this. Cut like this. We have a plane which cuts to middle. It comes to like this. Both the hydrogens, the mirror image of the other. Another plane, if this is the water, is the board plane, which cuts the molecule. Suppose if you have a water, this is a planar molecule. We have a plane here. What will we see on the other side? Same like this only. Same molecule. It is just the mirror image of the other. So all planar molecules have a default plane, which is the molecular plane. This you should always remember. Whenever you see a planar molecule, and what do I mean by planar molecule? Suppose you have a square planar molecule. I hope you know what is square planar. If you don't, we will come to you later. Suppose you have a PTCl for 2- molecule. This is a square planar. This also the molecular plane which passes through all the molecules. That is, whenever we have planar molecule, we have a molecular plane like water which passes through all the molecules. So remember, all planar molecules have a default PoS or a plane of symmetry. That is the molecular plane. Have a PoS. That is a molecular plane. All planar molecules have a molecular plane. All. Remember this. All planar molecules have a molecular plane. Another thing you must remember is a molecule can have more than one planar symmetry. Like here we had 2 planar symmetry. So you always have to look for all the planes of symmetry. But this is one trick, that whenever you see a planar molecule, it will always have a molecular plane as a plane of symmetry. That is one planar symmetry, you are sorted. You have to look at other planar symmetry. And the question arises is, how do we look at a plane of symmetry? We can draw an imaginary plane at any point. But we always draw the imaginary plane in such a way it divides the molecule into symmetrically equal halves. Again, as I said many times, is that whenever we choose a symmetry operation, we do it in such a way it divides the molecule into equal halves so that it maintains the symmetry. Right? Okay, let us look at the next molecule. We have a tetrahedral, suppose. This is a tetrahedral molecule. First of all, this is not a planar molecule. So this will not have a molecular plane. Tetrahedral molecules are not planar. Okay. So we have, this is suppose a tetrahedral molecule, like this is a 2D projection. We have a hydrogen here, a hydrogen on the top, a hydrogen at the below. So if we have this plane which passes through this top of the hydrogen, this below the hydrogen, then this hydrogen will reflect in here and both are hydrogen. Again, in tetrahedral molecules, this is another trick. Whenever you have 2 of the atoms are same in a tetrahedral molecule, it will always have a planar symmetry that passes through both the above the plane, below the plane, out of plane molecules, out of plane atoms. Again, I will say you, if we have hydrogen here and a hydrogen here, look carefully, don't forget this. Understand, carefully understand. We have a hydrogen this side, hydrogen here. We have a hydrogen top of the plane, we have a hydrogen below the plane. We consider a plane which passes through both these out of plane hydrogens. What will happen? It will reflect this hydrogen with this hydrogen. So in tetrahedral systems, when 2 of the atoms are same, we will always have a planar symmetry. Planar symmetry exists. When does it doesn't? Suppose we have this example. Now, if you pass a plane through both out of plane hydrogens, we have methyl on this side, chlorine on this side. Are they mirror images of each other? No. So this will not have a plane of symmetry with respect to this plane, with respect to here, like which passes through this methyl and chlorine. Absolutely, we can have a plane like this. Then these 2 hydrogens will reflect each other. That's why I said whenever in a tetrahedral geometry, any of the 2 atoms the same, it will have a planar symmetry. Plane atoms, if both the plane atoms are the same, then you will have a planar symmetry with respect to the out of plane atoms. If the out of plane atoms are the same and the plane atoms are different, you will have a planar symmetry with respect to the plane atoms. Then you will have a symmetry with respect to the plane atoms. Let us look at the last part of this molecule. Suppose I have a chlorine, methyl, fluorine, suppose OH. Will this have a planar symmetry? It's a tetrahedral. Again, what I say, in a tetrahedral geometry, if you are looking for planar symmetry, look for similarity between any 2 atoms. If you see similarity, it will have a planar symmetry. Here, are there any 2 similar atoms? We have a chlorine, methyl, fluorine, OH. No similar atoms. So this molecule will not have a plane of symmetry. Not even one. This molecule will have 2 planar symmetries. 2 planar symmetries. This will have 1 plane of symmetry, which passes through the in-plane atoms, reflecting the out-of-plane hydrogens. Suppose we have this, the outer plane atoms are different. Then we will have a plane which passes through the outer plane atoms containing both the methyl and such that it reflects both the hydrogens. So remember, in a tetrahedral symmetry, if two of the atoms are the same, we will have a planar symmetry. If two of the atoms are not the same, we will not have the planar symmetry. Two of the atoms have to be the same, not a planar symmetry. If all four atoms are the same, we have two planes of symmetry. Okay, then let us look at the next set of examples what we have. So suppose we have a cyclobutane ring, disubstituted by methyl atoms. Okay, let us suppose this is a cyclobutane ring. Suppose in the first example what we have is one methyl is at the top. In this case, one methyl is at the top, another methyl is at the below. Let's start with that one. Suppose one methyl is at the top, another methyl is at the bottom. Suppose I put a plane here which goes to the middle of the molecule. Suppose I draw a plane here, a mirror plane here. Okay, suppose I draw a plane here. It divides the molecule into two halves, right? This methyl here and this methyl here. But are they exactly mirror images? If one methyl is above, if another methyl is below, if we divide into two equal parts, will they be mirror images? No, right? That means for it to be equal, identical and to be mirror images, both the methyls have to be up, right? If both the methyls are on top, like here also the methyl is top, here also the methyl is top, and we put a plane in the middle, then we divide it into two identical halves which are mirror images of each other. So this molecule or this will not be a plane of symmetry. Rather, this will be a plane of symmetry. Why, you understood? So in all these cases, we will see the next one also. Suppose in this case also, the two substitutions must be on the same side of the plane. So a general rule is that both substituents or substituents must be on the same side of the plane for it to have a plane of symmetry. So if you can't figure it out by simple 3D projections, you must remember this, that if one of the substituent is above and another substituent is below, or if both the substituents are in alternate positions, then the molecule will not have a plane of symmetry. Only if both the substituents are on the same side of the plane, like I showed here, if both the methyls are on top, then only if you put a plane here, it will divide the molecule into equal and identical halves. With this methyl will show a mirror here. This methyl can't show a mirror here. This will not be the mirror image of this top methyl, right? So tell me now, in this case, which will show a plane of symmetry, this one or this one? You see for yourself, this one will show a plane of symmetry. This molecule will show a plane of symmetry. If you put a plane here, it will be divided into two identical halves with both the top methyls being the mirror images of each other. But in this case, if we put a mirror plane here, it will not divide the molecule into identical halves, since one of the methyl is above, the other methyl is below. These are not two identical halves which are mirror images of each other. So remember again, in these types of systems where you have two substitutions, again in this system also, next system, this will also have a plane which will pass through here. So whenever you have such symmetrical systems which you can divide into two equal halves, also look at the orientation of the substitutions. Only if both the substitutions are on the same side of the plane, either above the plane or below the plane, then only will they have a plane of symmetry passing through the middle of the molecule. In all these cases are same. You can have a cyclic system, you can have an acyclic system. So we talked about water, we talked about tetrahedral systems. Here we talk about both cyclic and acyclic systems which are symmetrical. See, all the systems are symmetrical. So you have something to divide the molecule into two equal and identical halves. In such cases, if both the substitutions are on the same side of the plane, then only the molecule has a plane of symmetry. This molecule has a plane of symmetry. This molecule does not have a plane of symmetry, this one. Similarly, this molecule has a plane of symmetry, but this molecule does not have a plane of symmetry. Tell me about this one. This molecule has a plane of symmetry, but if we draw the corresponding conjugate of this molecule with one methyl at the top and suppose the other methyl at the bottom, this molecule does not have a plane of symmetry. Okay, let us look at the last class of molecules. Suppose I have an alkene and I say I draw a plane here. It divides the molecules through a double bond to the middle of the double bond. We draw the plane. So this hydrogen will reflect here, this hydrogen will reflect here, correspondingly this hydrogen will reflect here, and the carbons are also reflecting. So I can draw a mirror plane through the middle of this molecule. such that both the hydrogens on the cis side will reflect each other. These are the cis side hydrogens, they are on the same side, cis side hydrogens. So cis side hydrogens or cis side substituents will reflect each other. If you are making notes, just write through this, then you will understand. Will reflect each other when we draw a mirror plane or when we draw a plane of symmetry. So if we draw a plane which divides the molecule into two halves, in an alkene molecule, the cis side hydrogens will reflect each other. I'll tell you something, this is another plane. You try to figure out what. I'll tell you in the next example what plane I'm talking about. But if you have figured out, you just stop this video here and figure out how this ethylene molecule is another plane. I am telling this is another plane. And don't tell me this is this plane. This also has this plane, not this plane. Apart from this plane, there is another plane. You try to figure it out. Let us see the next example. This is also the same as this one. The cis methyls will reflect each other. If we have a plane here and we are talking about the vertical plane right now, not the horizontal plane, okay? This doesn't have a horizontal plane, by the way. The methyl hydrogens will come. If we have a horizontal plane like this, the methyls and the hydrogens will interact and they are not identical. This is not identical. So this plane does not exist. But the vertical plane exists because the methyl will be reflecting and the hydrogen will be reflecting. So this plane of symmetry exists. Okay. Let's go to the next molecule. Now tell me what plane of symmetry will this have. I told if I draw a plane to the middle of the double bond, it will reflect the cis side substituents. Here the cis sides, there is methyl and hydrogen in both the cases, in the top also and the below also. But this is a plane of symmetry. You tell me how this is a plane of symmetry. Remember when I was talking about water, I told what? All planar molecules have a default plane of symmetry, which is the molecular plane. The molecular plane is a default plane of symmetry for all planar molecules. Remember, what is ethylene? It is a planar molecule. Ethene is a planar molecule. Remember? So this has a default plane of symmetry which cuts through the whole molecule, reflecting the molecule on the other side. As I told, spherical balls, just remember the earlier part of the video. So if this is the ethylene molecule, we draw a mirror plane here, such that this gets reflected, the whole molecule gets reflected on that side. So all planar molecules have a default plane of symmetry, which is the molecular plane. And remember, ethylene is a planar molecule. So this is a default plane of symmetry, which is the molecular plane. So when I said that this also is a plane of symmetry, this molecule also has a molecular plane. Whenever you see a planar molecule, as I told before, whenever you see a planar molecule, there is always a default plane of symmetry, which is the molecular plane, which cuts through the whole molecule such that the whole of the molecule reflects on the other part. So this is talk about ethylene. This molecule has no other plane, by the way. No other horizontal or vertical plane. It only has the molecular plane. Okay, let us look at the last set of examples before we finish the plane of symmetry. Suppose this molecule. Now this molecule has two planes of symmetry, I tell you. Now I tell you the number of planes of symmetry. You stop the video here, I'll explain the planes of symmetry. You stop the video here if you understood plane of symmetry and find out the two planes of symmetry. Okay, let's see it. Suppose I have a plane which I pass through here containing both the OH molecules. Okay, it will reflect this carbon with this carbon, and both are CH2 substituted, so both will reflect each other. Suppose this is a cyclobutane I'm talking about. Here is the OH, here is the OH. So it passes a plane that cuts through this molecule. So right, this part will reflect this part of the molecule, and both the parts are CH2. So this is one of the planes. Okay, in this case. Another plane is if you pass through this CH2. Okay. Suppose, as I said, this is the OH, this is the OH. Now I pass the plane through here, such that both the CH-OH will reflect each other. This OH will reflect this OH, and this carbon will reflect this carbon. Why this OH is reflecting this OH? Because both the OH are above. If one of the OH were below, the OH will no longer reflect. Then this plane does no longer exist. That is, the second plane I drew no longer exists, and that is exactly the second molecule. Here only one plane exists that contains both the OH molecules. This plane exists. But if we try to draw this plane which reflects the OH, this doesn't exist in this molecule. Because in this case, one OH is on the top, the other OH is below. This will not reflect, as we talked about symmetrical molecules. So this OH will not reflect this OH if you pass a mirror plane here. Both the OH have to be top, like both the OH have to be top, or both the OH have to be below in order for the mirror plane to pass, or in order to have a plane which is this side which cuts through both the CH2s. So this molecule has two plane of symmetries, but this molecule has only one plane of symmetry which contains the plane which passes through both the OH. So I hope you have got what is plane of symmetry. These are various examples, these are various classes of systems that are in the plane of symmetry. I don't think there are any more classes of systems in plane of symmetry. You try more examples of your own, you will come across various classes. If you think that we have not dealt with any of the classes, do let us know. We will try to include it in our videos, next video. I hope all the molecules you will encounter from now on to your exams will fall into these classes. Okay, the last thing I will talk about before we finish this video is axis of symmetry. What is an axis of symmetry? What is C in axis of symmetry? Axis of symmetry is an imaginary axis which passes through the molecule, around which a rotation of 360 by theta. What is theta? Theta is the angle of rotation. And if we rotate the molecule by 360 by theta, results in the formation of a molecule which is indistinguishable from the original. It is called the n-fold rotational axis and it is noted by Cn. What do I mean by this? Let us take our favorite example, water. Now, as I said before, and I have told this various times in this video, we always consider symmetry operations which divide the molecule symmetrically. So we have to choose axis of symmetry which divides this water molecule symmetrically. So we choose the axis here. Okay. We have to rotate the molecule in such a way so that this hydrogen after rotation will go to the position of this hydrogen and this hydrogen will go to the position of this hydrogen. So how do we rotate it? What is the angle you rotated? Suppose I rotated by 180 degree. I rotated by 180 degree. Then what will be the orientation? Then oxygen will remain in the position of oxygen. No problem. This H1 will come on this side. On rotation by 180 degree. And this H2 will come on this side. Suppose I have here. Okay, I have it here. And I put an axis here. And I rotate it by 180 degree. What happens? This is exactly what happens. Okay. So what is that? This is H1. Suppose the left one. This is H1. This is H2. Look at it carefully. Don't just lose H1 and H2. So H1, H2 we rotate by 180 degree. What happens? H1 goes to the position of H2. H2 goes in the position of H1. Now remember we are just numbering. H1 and H2 are both hydrogen. They are indistinguishable. Rotation of this by 180 degree results in a molecule which is indistinguishable from the original. So this can have a C2 axis. Why C2? Because on rotation by 360 by theta. What is a theta here? Theta is 180 degree. So Cn is equal to 360 by theta. So it is equal to 360 by 180. So we have a C2 axis. This is what I mean by Cn axis. We have a C2 axis. On rotation by 180, we generate a molecule which is indistinguishable from the original. So water molecule has a C2 axis. Why C2? Because we are rotating by 180 degree. If we rotate by 60 degree, we will have a C6 axis. Like an example of benzene. In benzene, suppose, if we rotate this molecule by 60 degree, this carbon or this one carbon come in the position of two carbon. So all the carbons will interchange their positions. So benzene will have a C6 axis. C6 axis. Let us talk about another example. Let us talk about ammonia. Suppose I have 3 hydrogens. Now how do I rotate this molecule so that both on rotation by some angle the hydrogens interchange their positions but they remain at the other hydrogens positions. You understand what I say? Suppose on rotating by some angle H1 goes to H2 and H2 goes to the position of H3 and H3 goes to the position of H1. What angle? Tell me. Suppose I rotate by 120 degree. You see on rotating by 120 degree, the H1 goes to the position of H2. H2 goes to the position of H3 and H3 goes to the position of H1. So we are rotating by 120 degree. So what axis is it? It is a C3 axis. So ammonia has a C3 axis because on rotating the molecule, suppose on here, on rotating the molecule by 120 degree, the hydrogens interchange their positions. But nitrogen remains where it is. And so it is a C3 axis. Why C3? It is because we are dividing it by 120 degree. This comes to 3, so we have a n-fold axis or a C3 axis. Now what happens is, okay, this is a little bit trick I tell you at the end right now. So suppose in some cases you can't visualize. Suppose what happens in some of the rotations, we can't visualize the axis. We don't understand, okay, this is rotating by this angle, but I can't visualize the rotation. So I'll tell you a small trick. In this axis, by axis of symmetry, on rotation by some angle, you don't have to know an angle, you just rotate the molecule such that it changes its position. Suppose you don't understand what angle it is rotating. So you just rotate the molecule. Suppose I have ammonia and NH3 and I don't understand, okay, it's rotating by 120 degree. So I just rotate it such that, so that I can get an indistinguishable orientation, the same orientation as before. So in rotating by 120 degree, rotating by some angle, see the nitrogen remains the same. Only the 3 hydrogens are changing their positions. Number of atoms which are changing their positions is the n-fold axis. Understand what I say? So here the 3 hydrogens H1, H2 and H3 are changing their positions. That's why it's a C3 axis. 3 hydrogens are changing their positions. So it is a C3 axis. C3 axis. See water, 2 hydrogens changing their positions. The oxygen remains as in where it is. So it is a C2 axis. 2 hydrogens are changing. So it is C2 axis. So this is a little bit trick that the number of atoms which are changing their positions is the n of the Cn axis. Let us take the last example. Suppose I have a BF3 and I don't understand what rotation will give me an indistinguishable orientation. Suppose I have a BF3, this is the BF3 molecule suppose, and I take an axis to here and I rotate it at some angle suppose. So that this fluorine F1 comes to the position of F2, F2 comes to the position of F3 and F3 goes to the position of F1. So how many atoms are changing their orientations? The bromine is as and where it is. Only the fluorines are changing their orientations. So if I don't know the angle, I can tell, okay, 3 fluorines are changing their positions, are interchanging among themselves. So that to bring about a molecule which is indistinguishable from the original. You have to remember, we are always looking for molecules which are indistinguishable from the original because we are looking at symmetry. We don't want to break the symmetry. So the molecule has to be the same as the original. So how many atoms are changing their positions so as to generate a molecule which is same as the original? 3. So it must have a C3 axis. Got it? So even if you can't visualize the angle, you just rotate in such a way so that you can understand, okay, this many atoms need to change their positions in order to generate a molecule or which is indistinguishable from the original. If you can understand how many atoms are changing their positions in order to generate an isomer which is indistinguishable from the original, you can say, okay, this is the n of the Cn axis, and then you just can get the axis. You don't always have to visualize the angle. Sometimes it becomes difficult for students who are studying for the first time in order to visualize angles. So this is a simple trick. So you just change the atoms and you see how many atoms change their positions. That is the n. This is a rule which doesn't hold good for linear molecules. Linear molecules always have a C infinity axis, because if we don't rotate it, if we keep it as it is 0 degree. We are rotating by 0 degree. So anything divided by 0 is infinity. Whenever you get linear molecule, what is the example of a linear molecule? Suppose I have ethylene. This is the easiest example. This will always have a C infinity axis which goes through here. So this rule or this number of atoms is equal to the Cn axis doesn't hold good for linear molecules. What happens for linear molecules? Linear molecules always have a C infinity axis. Whenever you see linear molecule, close your eyes and say, okay, it is a C infinity axis. You don't have to look at anything else. Okay. So we have discussed plane of symmetry. We have discussed center of symmetry. We have also discussed axis of symmetry. With this, we come to the end of symmetry operations. So I give you some things to work upon in your free time. So before we start the next video, I want you to finish this. So just find the POS. POS is the plane of symmetry and COS is the center of symmetry. Do this and come to our next video where we will start with optical isomerism and what is optical activity. From there on, we will go to optical rotation, specific rotation, and chiral center and stereogenic center. Thank you for listening to us. If you like us, do share, subscribe us, and do not forget to bring the bell icon for further updates.